Hi. So today let's begin the third chapter, which is the classical demand theory. So we'll skip the second chapter for now. So the third chapter, this classical version of the demand theory, it is based on the preference-based approach that we discussed previously. Okay, so that because the second chapter is a work based on the choice-based approach. Okay, so now we go first with this third chapter with the preference-based approach. Okay, so this is called classical demand theory. So before we introduce some properties, okay, on the preference relations that is going to be used for the consumer theory here or demand theory. So first, let's make it specific for this set of alternatives, okay, which is big X that we have previously discussed or defined. Okay, so here we say that this big capital X, the set of alternatives, in this case, when we're talking about or when we're analyzing the consumer's behavior, and then we specify these preferences over some commodity bundles. In this is called consumption set in this case. Okay, so this X, it is still the set of alternatives, but here it has another name called consumption set. Okay, so because we're dealing with or we're looking at the demand theory. Okay, we're looking at the consumption problem. So X, it'll be a subset, a capital X. It'll be a subset of L dimensional real space. Okay, so specifically, the element X, little x, will have will just be a vector with dimension of L. Okay, and all those entries are just positive real numbers. Okay, so you can imagine this as some consumption list that you're going to buy in a supermarket, right? So you're going to choose between how much you want to buy for the bread or how much what you want to consume on the milk, right? And how much you want to buy for the eggs, so etc. Right? So you have either zero or some specific amount of the positive number, let's say a real number of some certain good. Okay, and you put all those possible combinations into just a vector. Okay, good. So this still satisfies the definition for the set of alternative X, right? So it's just in this way, it could be helpful for us to further use this as some starting point to further compare across different consumption choices or different decisions, right? Consumption decisions. Okay, good. So that'll be some definitions to begin with. So here we have a brief review on the So here we have brief review on the in definition 3.b.1 on the textbook, which recalls the rationality for the preference relation. Okay, we don't bother to repeat this again. So next, in the other definition, then now we're gonna introduce the other new properties for the preference relation. So we say that the preference relation on this set of alternative X or on this consumption set X, and we call this monotone if the element X in that and another element Y. Okay, so here we use this notation. So this simply means that pairwise, each entry in Y is strictly greater than each entry in X. Okay, correspondingly. And if this implies Y is strictly preferred to X, okay, so if this is true, then we call this preference relation to be monotonic. okay, or monotone. Okay, so we have a similar definition, but there'll be a slight difference. Is that now we want to define another property called strongly monotone, okay, or strong monotonicity. So it's asking that if, so here we have each entry in y is greater than or equal to x, but those two vectors, they're not exactly the same. Okay, so there has to be at least one entry they're different. Okay, or the in y, that entry in y is strictly greater than that in x, at least one. Right. So, and if that's so, and this implies y is strictly preferred to x, and then this is the requirement for the strong monotonicity. Okay, so this strong monotonicity, it actually implies the monotonicity. Okay, so the second definition is a stronger requirement, and that's why it is called strongly monotonicity. Okay, strongly monotone, and that implies the monotone. Okay, so now let's have example, and that is mathematically, this is just a straightforward proof, right? So there will be only one step. Just use the definition. So to make this more straightforward, so now let's take an example. Okay, so let's say this y is a vector. Let's just put this as a column vector. Okay, so although we put it in a row, but here a column would be helpful for us to compare. Okay, so here we have this, let's say we have three entries. Okay, so x1, x2, x3. So now we have in y, those are 3, 2, 1. Okay, and in x, those will be the values with 3, 1, 1. Okay, so, and we can see that here, there's two, only the second element or the second entry in y is strictly bigger than that in x. And if we say that if a person thinks that y is strictly preferred to x, okay, so in this case, then this satisfies the requirement for the strongly monotone, right? Because we have something exactly the same, right? So this satisfies the requirement for strongly monotone, okay? And why we're saying that this could directly implies the monotonicity, okay? And this is because that here only one entry from y bigger than x is already enough for this person to think that this preference relation, or this is a strict preference relation, right? Y is strictly preferred to x. So that one entry bigger than that is already enough for that. Okay, so if all those entries are bigger in y compared to x, of course, if each entry is bigger, then this bigger or this greater sign implies greater than or equal to, right? So of course, this previous condition still holds. Okay. And now let's suppose that if we have this as 4, 2, 2, okay, so if each entry in y is all greater than the corresponding item in x, then this still holds. Okay, so that's why we're saying that the strong monotonicity implies the monotonicity. Okay, good. So now let's introduce another definition related to monotonicity, okay, and that is called local non-satiation or locally non-satiated. Okay, so we say that a preference relation on X is locally non-satiated if for every element X and every positive number epsilon, there exists some Y such that the Euclidean distance between Y and X, okay, so in this space of X, right? So this distance is no bigger than this epsilon, and this y is strictly preferred to x. Okay, so graphically, we have this little picture here to help us to illustrate or understand this idea. So we have this space of consumption set with x1, x2, and little x or little y are just 2 points in this space. So little x is this black dot, okay, and this y is this blue dot. So here this epsilon would be simply just the radius of the circle with the center of point x, right? So here this statement says that this preference relation is local non-satiated if for this x and some positive number epsilon there's some y such that there's the distance between those 2 points x and y is smaller or equal to less or equal to this epsilon, and this y is strictly preferred to x. Okay, so this would be the definition and the interpretation of graph for this local non-satiation. So what is, and later we'll talk about the why do we use this? Why do we need this local non-satiation? Okay, so before that, so previously we mentioned that strongly monotone, okay, so it implies monotone, okay, and monotone itself, it could further imply local non-satiation, okay. So and it is not difficult to show that, but intuitively, if again, so we're using the similar argument, the similar approach to show this, right, or to show the intuition of this proof. So if previously we have in the previous proof or this illustration here, we said that if this preference relation is strongly monotone, and we say that one entry bigger is already enough, right? And then all of those entries bigger will of course be enough as well, right? So if the conditions in strongly monotone, that is, if the conditions in monotone that is satisfied, then the conditions in strongly monotone will be satisfied as well, right? So again, similarly in this case, if the local non-satiation is satisfied, then the conditions in the monotone, so it means that pairwise each is bigger than the other one, that will be of course satisfied. Okay, so that'd be the rough idea behind this proof or this simple statement, right? So now let's talk about what's the meaning, or why do we even need this local non-satiation, right? So before that, we need to further define some things. Okay, so the first thing is called indifferent set. Okay, so an indifferent set that contains some element small x is a set of those y's. So those y's are the y's that are indifferent to x. Okay, so they have the same level of preference, and we say that define an upper contour set of element x, and that'll be all those y's which are weakly preferred to x, and correspondingly the lower contour set will be of x will be those y's that are less preferred or less weakly preferred to x. Okay, good. So now we are ready to show the meaning or why we even need this local non-satiation. So local non-satiation, essentially it helps us to rule out some sort of thick indifferent sets. Okay, so here we have this the first picture here. And this indifferent set is simply just the some set as we just mentioned, right? So it means that all those y's have the same level of preference as x. So here we have this black dot in the center. Here will be this x, and what is the y here? So all those areas here is the set of this y. Okay. Okay. So this will be the y. So here we call this indifferent set. This is thick, right? Because, right, literally. So this is the thick indifferent set. So we can see that the local non-saturation, if we have the thick indifferent sets, then this doesn't hold, right? So essentially, the local non-saturation, it helps to rule out the thick indifferent sets. Okay, so how about a normal or some consistent or some compatible preferences, right? That are consistent with the local non-saturation. So now let's take a look at this second picture here. So this x is still some point in this space with 2 dimensions, and this curve, this black curve, and noted labeled by this blue set, that'll be the set of y. Okay, so that'll be not thick or the normal indifferent set, right? So that has the same level of the preference as x. So how about what is the upper contour set? So that'll be just all those green areas, okay? Those y's that are weakly preferred to x. Okay, and so the correspondingly the red area will be just the set that the lower contour set, right? So those y's will be weakly, those x are weakly preferred to y. So this will be the lower contour set correspondingly. Okay, good. So this episode we discussed the strong monotonicity and local non-saturation. So, and we briefly discussed the underlying intuition behind those different properties. That is, the strong monotonicity implies the monotonicity, and monotonicity implies local non-saturation. Okay, and the local non-saturation, it helps to rule out the sort of the thick indifferent sets, and this will be not very useful for us to study the consumer theory. And we just want to have some single line or some not thick line as the indifferent set. And here correspondingly we have this blue, we have this green area as upper contour set, and this curve as indifferent set, and this red area as the lower contour set of some element x in the consumption set. Okay, good. So next video we'll discuss some other assumptions or some properties on the preferences, and which is called convexity. Okay, good.